In the PDDL section, in the corresponding video over there, we have actually seen how we can actually express with this specific representation language a domain and a problem. And we have mentioned over there that there are some kind of underlying algorithms that actually take these specifications and in a kind of a domain independent way solve the problem for us. They find, if you like, the optimal or some suboptimal plan that we're actually seeking to get. So in this video, what we will do is we will get to understand some first principles behind this kind of algorithms, which are based on what is actually called here forward search. And forward search is really, the most popular, if you like, method. Definitely does not really meet every single problem in terms of finding the optimal solution for every single problem we can actually pose to it, but it is able to help us out in a vast array of problems. So this is basically what we'll be focusing here. So the first thing I wanted to mention is that in trying to get into to understand these kind of forward search methods, many of you must have heard before about depth first, breadth first, or best first kind of search, the Dijkstra's kind of algorithms and so on. But we will be dealing with this, we will be treating those here just to make sure that everyone is on the same page. Before we actually get into those, I think it's worthwhile, mentioning that the PDDL had a factor representation in terms of state, and most of the treatment here will assume some form of an atomic state, and you can actually go from factor to atomic via a process that actually is called grounding, and you can actually create a graph-based representation that it will allow us to solve the problem. And this is what we will do now. In terms of practice, practical applications, we have, in the back of our mind, we actually can bring up the application of, let's say, route planning, or let's say of a vehicle. In fact, many self-driving car vendors and manufacturers are, they do implement this type of representation from, let's say, you have a car which has a camera and LiDAR kind of sensors, and that transformation from that domain into a problem where you can actually pose it on a two-dimensional map is very common. So here in the figure, you can actually see how the LiDAR sensing, which is evidently in the three-dimensional kind of space, and the camera sensing also in the three-dimensional space, ended up being a two-dimensional representation of a map. And you can actually see here, this map also has all the constraints. Let's say this map came from a parking lot, and the areas over here, the yellow areas there are areas where you cannot really go, but the black areas are areas where the vehicle actually can move. And therefore, with if you can imagine it, separating this space into a grid, and you can actually come up with something that will actually look like this. And so in that specific map, you have a starting state and a goal state. And your task is really to go from starting to the goal state in some satisfying some kind of utility. That utility, in some instances, it is associated with cost. You're all familiar with minimizing the trip time from going from a point to some destination in using, let's say, your Google Maps. Or it could be also be posed as a gain. And later on in some other videos, we will see that this gain could be associated with some quantity that we call reward. So it's always good to have it in both ways in your mind in terms of the cost. So from that kind of abstraction, we will be going and creating, if you like, next we create, if you like, a graph. And let's see how that is going to be done. In general, we're going to have the following situation in all of these problems we're dealing with, is we're going to have some kind of a node that represents a state that we are in right now. Let me call this S. then there will be, from that kind of state, if you remember the discussion about preconditions, there will be definitely some actions that we will be able to take, and these actions are going to be denoted here with just solid circles. That's a common thing to do in MDP, reinforcement learning kind of community. Not so in the planning community, but we'll just adopt this notation. So these are basically all the possible actions we can take from the state S. And each action will actually lead us to a number of other states. And this thing is also called the sort of the branching degree. Okay, how many branches are we going to be generating out of an action that we're taking from, let's say, a state? So as you can understand, there is going to be potentially exponential kind of explosion of the possible number of states that we have to visit in order to find, if you like, that optimal kind of plan. And this will actually be a problem that we will need to actually solve, and the various algorithms in their the one that are actually implemented in practice, they do solve for us using heuristics. So the problems are of such complexity that without heuristics, it's almost impossible to find in a reasonable time solutions. So we will be calling these states that we are reaching from, let's say, a certain action S prime. And this is called the next state. The prime stands for next state. All right, so just to put some kind of numbers, if we had, the branching, let's say, in general of n, and our, as you can imagine, there will be more and more sort of actions and so on that we will be able to have from a given, let's say, state. H double prime is the state that follows, and the solution is, let's say, down d steps. Then in general, we will have n to the power of d nodes in our search tree. So as you can understand, the even with a simple block sort kind of problem, then we have an unbelievable amount of nodes that we have to actually visit in order for us to determine the solution to the problem. So that's basically the search tree that we will be with us. In general, we will be dealing with graphs. And in most instances, the graphs we will be dealing with are going to be, do not necessarily have loops. So we'll actually also make that kind of assumption. And on the right-hand side over here, I'm going to quote a very general forward search kind of algorithm that is going to be the solution for searching. And the algorithm is going to be general, but then it will accommodate many of the well-known kind of search algorithms, such as the depth, the breadth, and the Dijkstra's kind of algorithm, and introduce what ends up being called dynamic programming solution to these problems. Okay, so that dynamic programming is quite important to get it in this kind of video, because it will be used in subsequent videos when we're dealing with Markov decision processes. So the algorithm goes as follows. So we have some inputs. These inputs will, as we discussed, is going to be called, instead of an S prime, let me call it S, the initial I for initial, and SG for the goal state. Okay, so then we define the first step. The first step is we need to have a data structure that we'll be calling priority queue. So the priority queue, and we understand, I mean, everyone is familiar with the concept of a queue, but what is called priority queue is going to be discussed now. Priority queue, we will call it Q, and this priority queue will have two methods that we are of interest to one. The first one is the so-called insert method, and we will insert at this point the initial kind of state. And we also going to have in this kind of queue, this insert method will effectively mean that this state that we are inserting is visited. Okay, so let me write this over here. Mark SI as visited. And the second step is a while loop. And this while loop is while the queue is not empty, we have now the sort of, let me call it A. The step over here is that we are producing an next state, let's call it S in general, from the picking up from the queue the highest priority element. Okay, and so the queue is not like first in, first out, as it is normally the case from as you kind of line up in a store to, let's say, to buy coffee. But it is can have a policy which is quite different than FIFO. Okay, and in general we call this in this get first, whatever that policy is, we are effectively retrieving the highest priority element out of or state out of that queue. So we are getting into the next state out of that kind of method. And if it so happens that S is belongs to the set, let me call it capital S, of goal states, the set of goal states is S capital SG, then we can return that we have a success and we have a plan in our hands. Okay, and but if not, if that top highest priority element is not one of the goal states, we have here the third. So we are returning and the for search kind of terminates. But if we this condition is not satisfied, then for that S, what we will do is we have a for loop for A, for the action to belongs to the set of actions that can be taken out of that kind of state S. So the set of actions that can be taken out of that state S is this guys over here, 1, 2, 3 in this case. So for each one of them, we are getting that next state S prime out of some form of a transition model. We have seen this transition model being quoted when we did Bayesian filtering, in that kind of Bayesian filter or recursive state estimation algorithm. When we discuss in that kind of video, we have seen this kind of form of a transition model. So we call this transition model F. So someone is determining for us where we're actually are going next, what state are we going to hit next for that specific action if we are in state S. And if S prime is not visited, then we mark S prime as visited. In fact, we call it as visited or explored. In your notes, it is explored, so let me write this down as explored. And we are inserting this into the queue with the usual insert method that we have also quoted over here. And else we have a method that's called resolve duplicate S prime. So we have in general three types of states. In the so-called forward search. The first one is the so-called unvisited states. In the unvisited states are such as the starting state that we just started. Evidently, these are states that we have not really visited yet. So when the initial the algorithm kind of starts initially, all of the states except from that initial state is in the unvisited, if you like, set. The second kind of category is states that we have a so-called dead states. These are dead-end states. These are the states that have been visited and for which, so let me write it down. So visited and all states that can be reached via actions, obviously, from those are also visited. Okay, so there is no, in other words, they call them dead because they cannot really contribute anything to the search kind of procedure. And this is the third category. As you can understand, we call them the so-called alive states. Alive, and these are the states that they have potentially encountered. We have visited them, but there are states that we have not visited for those nodes, for those states. So therefore, we keep them in this kind of list because we would like to. We call them alive because we would like to do something with those nodes. Okay, so the only alive state initially is the starting state, and these are the states that we store in priority QQ. So I hope everything is clear now as to what are the things that we need in order for us to implement the forward search. But I think I forgot to mention something about this line here. This resolved duplicate S prime means that when S prime has been visited before, we may need to resolve. And so in some algorithms, we have, by resolve, we mean some kind of an update, resolve update, some metric, let's say the cost associated with the state S prime. Associated with S prime. So that is really the job of that kind of last line of that kind of forward search kind of algorithm. Okay. All right. So now that we have, if you like, the structure, then we will actually can go and see what kind of policies we can implement, priority policies we can implement inside that kind of queue, and how the algorithms that we have been sort of known in the past, like depth and breadth search, first search, are kind of derived out of that kind of general algorithm. So let's look at depth first search and the specific instance of this kind of priority queue there. So let's assume that we have, if you like, a problem. Let me give you a problem. This is a graph. Let's say the states are just capital letters here. And you can understand, how this also could be associated. Later we'll see some kind of a minimum cost type of algorithms as well. So right now the edges are not weighted. So this is the input kind of graph, and we would like to actually get into the following sort of a goal. So what is really the starting state? The starting state is state S. So that is our starting state, Si. And the goal state is, let's say, the goal state is C. So let's look now some kind of specific policies and what kind of names we can associate with them. For example, the policy LIFO, or last in, first out, corresponds to what we call the depth first search, which I'm sure you have heard before, DFS. So here we have a small problem. We have a graph. We have some kind of initial state S and some goal state C. And what we actually have done over here is we actually drew a table that in one column we have the order of visitation, what kind of, in other words, state we're going next and in what order, and the other is the contents of the priority queue that we have seen. And so starting from the starting state S, we are visiting S, and we, in the priority queue, we are storing all the nodes of the graph which are adjacent to S. Okay, so we have effectively nodes E, D, C, and A that we have actually storing into that kind of queue. And given, if you like, some kind of policy LIFO, let's assume that A was the last state that we have stored, then we will go and visit that first, because that is basically the state that the priority queue returns to us, the so-called get first method. And for that specific state A, we are effectively determining over here we are adding into the priority queue the nodes which are adjacent to A, and we have, so the only node that is adjacent to A that is not really the S that we have already visited is B, so we add this into the priority queue. And given again the LIFO kind of policy, B is returned, and therefore we are storing effectively nothing into the priority queue. We're not really adding into the priority queue because C is already included. And so the next LIFO method is going to return C. And so the last element over here that we added is going to be visited next. And for C, C is actually also our goal state. And the algorithm kind of stops there. Okay, so this is basically SABC is really the plan that results out of this kind of exercise. However, obviously you can understand this plan is suboptimal, since already we could go from S to C directly. Okay, so that's basically the exercise. In terms of a search tree, I have drawn also here the search tree. As we discussed, we are starting from a node S, and therefore we can actually go with with cost 1 to A, C, D, and E. So the sort of depth first search will stop when either the plan is found, if we are just have a query such as find all of the nodes which are sort of adjacent or reachable from the starting state, from a state S. If that is the query and it's not necessarily, we don't have a specific goal state, then the algorithm will actually continue and until the priority queue is empty. So mind you, in the literature you will see also this search tree being produced. We do not expand C because that's our goal state, or E because we already have visited that E when we exploring D. Okay, so that is basically our search tree, and as you can understand, the depth first search, that's where the name came from, favors deep explorations from the get-go, and as compared to another method we'll see now called breadth first search, where effectively the policy there is FIFO. So looking at the equivalent, if you like, sort of table, we can actually see that yes, we have the so-called A, C, D, and E. But here in the kind of a FIFO policy, what we do is slightly different. So for us, we're going to write now the A, C, D, E as we have seen it earlier. Also, and then if this was a LIFO and A was resulting out of it, then the first element here is, let's say, E. And so we can actually visit E. And as far as E is concerned, then we have nothing to add. So it is A, C, D. All right. So then we will go into D. And in this D, we have nothing to add also. So we have A, C. And then we will go into C. And C will be the goal state, and this algorithm will actually terminate. So mind you, I want to mention that the order of visitation does not mean necessarily that there is also a plan. It just so happened that the plan was also according to the order of visitation over here. But in order to get into the plan, what you need to do is you also need to store the parent of every node that you are actually visiting and evaluating. And therefore, out of that kind of a parent relationship, then we will get the C has a parent of S, has a parent S, and therefore that is really the plan. So the plan in the breadth first search is very straightforward to get, just when it, because the C is within one expansion from S. Now, again, if we are to draw the whole tree, kind of how it is going to be traversed, then apparently if the algorithm kind of continues over here, then we will be visiting also A. And then A has a node that has not been inserted in the queue yet. Therefore, A, we will also insert here the B, and that's basically the call tree transversal of the BFS algorithm. Up to this point, we have seen a couple of algorithms, and now the third one, which is actually quite important, as it's a special case of an algorithm called dynamic programming. So this is actually called the well-known Dijkstra's algorithm, and let me call it as a special version of dynamic programming that we will be also be discussing in Markov decision processes. So to motivate this kind of dynamic programming or shortest path algorithm, and it's sufficient to actually observe from the previous kind of discussion that in many cases that kind of priority queue, let's say a LIFO, did not result into an optimal kind of path, and maybe the breadth first search also didn't. It's just that in this specific case where the graph was too simple, did. So Dijkstra's though has been shown that it is going to find, let's say, the optimal paths throughout, if you like, a graph, and that's why it is a very, I will call it, popular algorithm in many of these settings that we are dealing with. So to motivate that kind of algorithm, we will be dealing with a graph, which is slightly different. This graph will actually also have edges which are, I will call it, directional also, and also have costs associated with it. So let me just draw the graph over here. So I have this kind of a starting state S. So we have A with cost 1. A, B is from A with cost 6. Then we have some target or goal node, which is has a cost of 2 from B to E. So this is the graph over here. Okay, so this is the problem statement here is calculate the minimum cost path from S to all other states. Okay, that's one kind of problem statement that we will need to solve here. And so we have the graph. The graph has these vertices. This is S, C, A, B, D, and E. And obviously it has some kind of edges. So the first thing that we are doing is to linearize the what is called directed acyclic graph. Probably notice we have no loops over here, so we have a directed acyclic graph. So we linearize it in a sense that we are going to create a new graph that is going to have only edges that are moving from left to right. Okay, so the graph is like this: S, C, A, B, D, E, and from B to E we have one more edge. We have from C to D one more edge, and we have from S to A another edge. Okay, so this one has cost 3, cost 1, cost 2, and this is 2, 4, 6, and these guys are 1. Okay, so in this kind of linearization exercise that we have just done, we got, if you like, a graph that is sort of going to be far more helpful than the graph over here to come up with an optimal, if you like, scheme to solve this kind of problem. So what we are actually going to do is we will be designating as all costs with the capital C. So the very first step is to initialize all costs with a letter designated with the letter C, and this is from cost from state S to all other states as 0. Okay, and evidently the let's say CSS is equal to 0. And then the second stage is for all, it's a for loop, for all vertices V that belongs to the set of vertices capital V, except from the starting vertex S. So this is backslash curly brackets S means except from S in the linearized order. Calculate the following equation. C SV, where V is this vertex that we have in the for loop. Calculate this as a minimum of U, V, which are the set of vertices that the pair of vertices which I need to define, which belong to the set of edges. I forgot that there's also a set of edges over here with all the edges that we have in the graph. So for all the edges, if you like, so we take the minimum of quantities that are associated as the cost. Let me call that edge cost, plus total cost until node u. Total cost until node u. Okay, so let me replace them with some kind of variables. We can associate a bit better the equations. U comma v belongs to edge, set of edges. The edge cost, I will call it as C uv, and the total cost, I'll call it the C su. Until the node u, I will call it as CSU. And this formula makes complete intuitive sense to me, as it basically says to us that, you know, the cost from S to V, let's say the cost from S, let's say, to D is the minimum of the cost from S to B plus the edge cost. Is the minimum of the total cost until we reach the node B plus whatever that cost is, plus the edge from B to D. Okay, so this is the minimum. Okay, so the minimum over all of these will actually be determined now step by step. So we will start from a problem that we already know the solution, and the problem we don't know the solution is this one. So we can just repeat it here. CSS is equal to 0. And the next node over is the SC, which according to this kind of formula is the minimum. It's not really a choice here because there's only one edge that goes from S to C of what we have here as just CSS plus, let me actually write the edge since I wrote the edge first in the equation. It is CSC plus CSS. So there's only one term here, so this is basically 2. All right, so because CSS is 0. So then we have the other node, which is this cost to A, CSA, is the minimum of the edge from C to A plus the CSC, comma. The other one is there's a direct path from S to A, so this is basically CSA plus CSS. So we have here the cost CA is 4, the SC is 2, so this is minimum, and then the other one is 1, and therefore the answer is 1. And the same thing can actually go into repeat this exercise that we have done for all other nodes. Let me write one more. So this is B. And as you can understand, we are actually reusing earlier results. So that's the sort of value of dynamic programming, if you like, to reuse earlier results that we have obtained. In other words, we are converting, if you like, a global problem of calculating the minimum cost, let's say, path from S to other nodes into a sort of many local problems that we actually know the solution. Either we know the solution already, or we can, it's very easy or trivial to calculate the solution. And then we are gradually expanding into more and more complicated problems as we move along this linearized kind of graph, reusing earlier results. So we have seen this reuse over here. the 2 was reused over here without really having to solve anything else. We can just replace it. And now we will see it also over here. This is the edge from A to B plus the cost from SA. There's nothing else going into B. So this is, now that we have that, is the minimum of A and B. The A and B, A to B is 6 plus 1 is, the final answer is 7. And so on and so on. So we can actually continue to calculate all of the costs associated with it and reach, if you like, nodes which are fairly far away from S by effectively calculating the cost to D, the CSD in other words, and then adding, if you like, the 1 over here, which is the edge, and that compare that and taking the minimum between the CSB and adding that edge of 2, and which one is going to win that kind of minimum comparison also will give us the SC at the end of the day. Okay, so this is exactly identical to what all the calculations we have done earlier. How this is related to what we have met before, this priority queue and the selection of the election of new states S primes out of prioritization of the queue. Well, it is related as follows. The priority metric in the queue is the pass cost, as it's called, or cost from the beginning of the initial starting state, if you like, to the specific node that we have there in the graph. So we are actually prioritizing the queue, and we are ranking, if you like, or sorting the elements of the queue, which are effectively nodes in the graph, according to this metric over here. So we're always effectively picking up from the queue the one which has the minimum possible cost from the beginning of the problem until the point that we are right now. And this is basically what we are mark them as visited nodes. And then how we actually proceeding is we're proceeding in a very similar way to that general flow that we have seen earlier on in this discussion. So that's how the Dijkstra's kind of algorithm with the priority queue are kind of connected. In fact, it's the priority queue is really the implementation of the Dijkstra's algorithm, where priority is that kind of a past cost. As we'll see in a moment, there are two things that we should be concerned with. One is the sort of the past cost, and we have versions of the algorithms that we actually will be calling A star that are actually dealing with estimates of future costs. In other words, estimates from the node that we are right now to the let's say a goal node, if we have that in our problem. And that's what we will be dealing with right now.